Okay, last round. So yeah, I want to wrap up everything with a discussion of the singularity theorems. I wouldn't feel well if I would leave this topic out completely, because it's one of my favorite topics, and actually I think a very essential topic in view of cosmology. So I want to spend a certain time on that. I think I will use maybe 45 minutes or so on that. And then, if you like, there's time for questions after that. And then we call it a day. So we will now talk about the singularity theorems. So what's the issue? The issue is that one had observed in various different situations in general relativity that singularities are formed. So there was, I think you all know the Oppenheimer-Snyder collapse, where you have a dust ball, was calculated in the 1930s by Oppenheimer and Snyder, and you let it collapse and it forms a point singularity in a finite time. Well, at that time people said, okay, if you have spherical symmetry and you have dust, what else should it do other than forming a singularity at a point? It would also be in a Newtonian situation like that. Yeah? Also in Newtonian theory, a ball of dust falling under its own gravity would form a point singularity. But in Newtonian theory, as soon as you switch on a little bit angular momentum or perturb the spherical symmetry in any other way, then there will be no longer a singularity. Then the thing would start to oscillate around the center and maybe to re-expand or doing any other things. And people thought maybe in general relativity it's similar. So it's just an artifact of the high symmetry. And also in cosmology, well, we have talked about many solutions of Einstein's field equation in cosmology. And all of them, if there was a matter content, all of them had an initial singularity. Yeah, so in particular, the Einstein de Sitter universe, which was considered to be a realistic world model, say between 1930 and 2000 or so, this starts with a Big Bang. But also in this case, people thought, well, that's an artifact of the symmetry. We assume perfect isotropy, perfect homogeneity. So as soon as we perturb the symmetry a little bit, there will be no longer an initial singularity. At least that was the hope. We have also done the Bianchi models, where at least the isotropy is dropped. And we have seen also there is a singularity. So maybe the singularity is more generic as people thought. And this was a discussion which began in the 1960s. So the question was, how generic is a singularity? Or how generic are singularities in Einstein's theory? So do they occur only for very special solutions, with very special assumptions, over-idealized assumptions, high symmetry, and so on? Or do they occur in a certain sense generically? And there were two different developments simultaneously in the 1960s, which made important progress in view of answering these questions. So the results on this question were mainly done between 1960 and 1970. And they were done by two groups in two different political systems, one in the Soviet Union and the other one in Western Europe, mainly in England. So the first group was a Landau group in Russia. The people involved were in particular Belinsky. This is, what's his first name? Volodya Belinsky. Isaac Kalatnikov. And Yevgeny Lifshitz. I think you all know the name Lifshitz because he is a co-author of this textbook series with Landau together. Landau was the head of this group, the big boss, and they were collaborators of him. Actually, Landau was still alive. I think he died in '67 or so. But as you maybe know, he had a traffic accident, so he was comatose for several years even before he died. So I think he didn't really take part in this discussion. So, and the other group, of course, you all know these names. These were Roger Penrose and Stephen Hawking in particular. So Penrose began this work alone, and then the PhD student Stephen Hawking joined in, and that's the work with which Hawking became famous. So the methods were completely different. What the Russian school did was they studied initial conditions. So they gave initial conditions for Einstein's field equation with a certain matter content, and they try to find out how should I choose the initial conditions so that a singularity is formed. Is this a very particular, a very small set in the set of all initial conditions, or is it more or less a generic? Is it more or less, is it the set of measure 0, or is it the set where the complement is of measure 0? That would have been a very, very nice answer. So the idea was to study initial conditions. Find out conditions such that a singularity is formed. This may be a future singularity or a past singularity. Yeah, if you're interested in the collapse of stars, then of course you would look for a future singularity. If you are talking about our cosmos as a whole, of a cosmological model, then you would ask about past singularities. And well, in the first, I think it was the first, or one of the first papers from this group, it was by Kalatnikov and Lifshitz alone, they claimed that the set of initial conditions is a set of measure 0, which gives the singularity. So that singularities would be very special. That generically there would be no singularity. But this result was false. It was just a mathematical error. And they draw it back a little bit later. And in parallel, there was a work by Hawking and Penrose, which showed exactly the opposite, which they used different methods, but it pointed in completely the opposite direction. And after a couple of years, also the Russian group agreed that, that also their methods seemed to indicate that singularities are generic. But I think it's fair to say that they never proved a mathematically rigorous result in this direction. Yeah? So from the Russian group, there were indications that singularities might be generic, but nothing which could be really called a mathematical theorem. The Russian work was important for a different reason, because their method was able to show in which way the singularity is approached. So for certain assumptions, they could show that actually the Kastner metric, which seemed to be very special, that actually this plays an important role for generic singularities. That you have, under much more general conditions, you have something like Kastner periods, where if the singularity is approached, the behavior is very similar to the Kastner universe. This was one of the results of the Russian group, and other results about the way in which the singularity is approached came out of their results. So in this respect, it was important and successful. But in view of the question of how generic singularities are, I think the second approach was much more important and much more successful. And for this reason, I will now talk about the Penrose-Hawking singularity theorems. So their methods were completely different. The idea was to prove theorems that singularities occur in spacetimes that satisfy some generic conditions. And I put generic in quotation marks because, of course, it's always a matter of debate. What does generic mean? So they made assumptions where, most people would agree that a reasonable universe should satisfy these assumptions. So they are typically, let me continue here, typically the following kind of assumptions. There are different theorems, essentially 4 theorems. I will concentrate on 2 of them in this lecture. So typically, there's a comma here. So energy conditions. So the energy momentum tensor should satisfy a certain property. So there's one condition which you have maybe heard about is a weak energy condition, that the energy density should be positive for all observers. That would be an energy condition. Or another one is a dominant energy condition, that the energy flux should be subluminal. So that the energy shouldn't flow with a speed bigger than the speed of light, which is a very natural assumption. And there's a third one, which is actually the one which will occur in the theorems I will discuss. This is the so-called strong energy condition, which means that gravity makes freely falling particle converging. So if you have a cloud of dust particles, and you let it go under the influence of the gravitational field, maybe of matter, which is distributed around it, then they will not make divergent, but rather they will come together. So this means the apple falls towards the Earth and not away from the Earth. That's what it means. So if the gravity field has this property, then this could also be formulated as an energy condition, and this will be the one which will occur in a minute. Then they had topological assumptions. So one of the Hawking theorems, for instance, applies to a spatially compact universe. Yeah, where you have a spatially closed universe. In cosmology, you would think of this being, for instance, a three-sphere, but you could also think of a three-torus or something like that. So such an assumptions are also causality assumptions. So that there should be no closed time-like curves or things like that. That's the third kind of assumption. And then the third is a converging or diverging initial condition. Or let me write, maybe I should write collapsing or expanding. That's, I think, clearer what I mean. Collapsing or expanding initial condition. So that at one time, for instance, if you think of cosmology, that at one time our universe should be expanding. And that's what we observe, actually. So the third assumption would also be very natural in view of cosmology. Or if we talk about a star, then we just assume that it starts collapsing. Yeah? At some time, it has a tendency to, the particles which form the matter have the tendency to converge. And then, if the assumptions are properly combined, then a singularity would be formed. So it's not the way that the singularity would be avoided. The particles would circulate around the center or maybe re-expand, but singularity would be formed. Okay, so that's the idea. So proof theorems of this kind, and well, they worked really hard on this on this issue during this decade, and as I said, they proved a number of theorems. Some are particularly relevant for collapsing stars. The first one by Penrose was aiming at the collapse of a star. Then there came two by Hawking in '67, which were mainly about cosmology. And then they wrote a joint paper about a fourth theorem, which applies to both situations. And I will here, in the course on cosmology, of course, I will concentrate on the Hawking theorems. And well, before stating the theorem and then discussing it a little bit, we have to talk about the question: how are singularities defined? Actually, I think this was one of the most important steps in this work by Penrose and Hawking, that they define singularities in a particular way. It's not quite clear how you should do this in general relativity. If you think of, say, electrodynamics and special relativity, you have an electromagnetic field, you have charges, currents, and electromagnetic field. It would be fairly clear what you mean by a singularity. The field strength should become infinite, yeah? Or the charge density should become infinite. And this would become infinite at a certain point in space and time. Yeah? So you could consider sequences which converge towards a particular point, and if then along this sequence the density or the electromagnetic field or whatever goes to infinity, then you would say there's a singularity at this point. But when we do general relativity, then the quantity which we are interested in, the mathematical field we want to discuss, is the metric which gives the geometry of space-time. Yeah, it's not something which lives on the background. It is the geometry of space-time. So if something is bad with the metric, then the space-time is not defined at this point. So it's not a point in space and time. It is something which is outside of space and time. And for this reason, this method of considering sequences which converge towards a certain point, and we see if something goes to infinity along this sequence, this doesn't work, this method. Because if there is a singularity, then it is outside of the space-time. It's fairly easy if we have homogeneous cosmological models. Then we use just the slicing into these homogeneous subspaces. We have the proper time coordinate along this, and we would say there's a singularity if the density goes to infinity for a certain proper time value back in time. But if you have a space-time without symmetry, Then you don't have this slicing, you don't have this proper time coordinate, and it's much more difficult to define what you mean by the fact that something becomes infinite. If the quantity you are interested in is not part of the manifold, at this point the manifold itself is not properly defined. And for this reason, Penrose and Hawking defined the singularity in a completely different way. Nothing about densities becoming infinite or curvature becoming infinite or something like that. As a characteristic property of a singularity, they use the fact that a time-like or light-like geodesic cannot be extended beyond a certain point. Where this is quite natural if you have extendable spacetimes. You think you are in Minkowski spacetime and you remove just one point. Yeah? And it's still a reasonable general relativistic spacetime model. Somewhat contrived, but it is an allowed model. And now we can consider all kinds of geodesics which tend towards this point. And of course, if you follow the proper time parameter along time-like geodesics or the affine parameter along light-like geodesics, they will terminate here at a finite value. And you cannot extend them any further. In this case, you would say, well, this is just a trivial kind of singularity. Fill in the point again, and then everything is fine. Yeah? So if this happens in an extendable spacetime, then nothing is bad. But if it happens in an inextendable spacetime, where it is not possible to extend it beyond the point where the geodesics terminate, then something is really bad from a physical point of view, because a proper time along the geodesics is really the ticking of a standard clock, of a freely falling observer. And if an observer arrives at finite time at the end of the world, then something bad happens. Yeah? If just the world stops for him because his world line cannot be extended, then you would say this is a kind of singularity. And that's the definition which Penrose and Hawking used. And it was not possible to restrict to time-like geodesics. That would have been nice. But they had to use also the notion of light-like geodesic incompleteness. So at least for some theorems, you cannot predict the time-like incompleteness, but only time-like or light-like incompleteness. And now there's a matter of debate. Is it really physically unavoidable to require from a reasonable space-time that the light-like geodesics are inextendable? Because photons don't have clocks. Yeah, there's no proper time along the world line of a photon. The affine parameter, we usually say, is just a mathematical tool for parameterizing the world line, but it doesn't have any direct physical application. Nonetheless, you would also have the feeling if a photon arrives here at a finite affine parameter that the life of a photon in a certain sense ends all of a sudden before really the full extent of the parameter is exhausted. So in a certain sense you might also say that this is a kind of singular behavior. And maybe you know already, yes, I'm sure everybody of you know examples of spacetimes where you have a singularity, think of black holes, a singularity at the center where time-like geodesics terminate, where light-like geodesics terminate, but not time-like geodesics. So Schwarzschild, if you remember, if you fall into a Schwarzschild black hole, you arrive at the singularity in a finite time. Yeah, I think most of you have done this little calculation, how long time it takes if you have crossed the horizons and to arrive at the center in free fall. And you will arrive there in a finite time, and also a light ray will terminate at a finite affine parameter. But then there's another black hole spacetime, I think most of you will know it, where if you are freely falling, you avoid the singularity. You will not reach the singularity if you are freely falling. But photons actually will reach the singularity in a finite affine time, if you might call it. Anybody remember which spacetime this was? It's Reisner-Nordström, exactly. Yeah? If you are freely falling, you avoid the singularity. You will end up in this other universe. So you leave over a second horizon, the interior part, and you end up in another universe. But if you move at the speed of light, assume you could do this, and you are freely falling, then you end up in the singularity. And because these situations are also possible, one has to include the situation, the case of light-like geodesic incompleteness. So the definition of a singularity is space-time is singular or contains a singularity, or whatever you like to phrase this, is singular if it is inextendable. So you don't do something like that you just remove parts of a nice and reasonable space-time. It's inextendable, but either time-like or light-like, geodesically incomplete. Yeah? So this means the affine parameter along the geodesic cannot be extended over all values from -r to r. Well, the notion of geodesic completeness or incompleteness was very well studied at this time for positive definite metrics. This goes back several decades from this time, 1960 or so. And for positive definite metrics, there's a famous Hopf-Rino theorem, which says that a Riemannian positive definite manifold is geodesically complete if and only if it is metrically complete. So if and only if you have, with a Riemannian metric, you can measure distances, and if with respect to this, metrical measure, the space-time is complete. So this is very, very clear-cut and easily remembered results. It's much more difficult in the Lorentzian case. Yeah, to study geodesical completeness or incompleteness in the Lorentzian case, it's much more difficult. And at the time when Penrose and Hawking studied, this actually didn't exist. In the course of developing these theorems, the people developed this kind of mathematics, and then later textbooks were written. Maybe some of you know the textbook by Beam and Ehrlich, which is one of the standard works on Lorentzian geometry. And there, all these notions are then discussed in great detail. But around 1960, this didn't exist. This was really developed in the course of this study. So it was something which is pure mathematics, but it was motivated by this physical question, and it developed into an important mathematical field. So our goal is now, we want to prove, or the goal of these two gentlemen was, they want to prove theorems that if a certain kind of assumptions are satisfied, typically 3 assumptions of these 3 different types, then the space-time is time-like or light-like geodesically incomplete. And if you really follow the geodesics as far as you could, then of course you would get something which is inextendable. So if this also occurs under assumptions here on this, think of the Minkowski space, you remove just one point, you state theorems about the manifold with this point removed, then of course you could never prove that the space-time is geodesically incomplete, because the conditions on this rest of the space-time, they of course don't know that you have removed the point. Yeah? So this issue is automatically taken care of if you formulate the theorem in this way. Okay, and now I just state the 2 Hawking theorems, and then we discuss them a little bit. So the first one, both of them were proven there was a series of papers by Hawking, 1966, 67. I think it was 3 papers altogether. In the first one, there's an error. Yeah, he proved the theorem, and then in the third part he says, oh, this was wrong. So now I correct everything. And the essential results are in the third paper, which is from 1967. So this is a theorem which was proven by Hawking in 1967. And the first theorem I want to quote here is about spatially compact universes. And I think it is, as far as the formulation of the theorem is concerned, it's the easiest of the singularity theorems. Not as far as the proof is concerned, but as far as the formulation is concerned. So I think in this case, all 3 conditions can be easily understood. And the theorem says, space-time is singular in this sense if the following 3 conditions are satisfied. So the first condition usually is an energy condition, and in this kind it is the condition that freely falling objects and also light rays are made convergent by the gravitational field. Of course, this doesn't mean that they always converge. If you give an initial condition that they are moving away from each other, then of course the statement is that the expansion is reduced, that it becomes smaller. But if you let them just drop, so you start with a dust ball at rest, and you just let it go. Then, under the influence of a gravitational field, it would make convergent. And the mathematical condition is that the Ricci tensor, I've used Greek indices, right? K nu is bigger, convergent, or just the borderline case. It is also allowed for vectors K mu, which are time-like or light-like. Yeah. So this means, in particular, so think of what's the meaning of the curvature tensor. Ricci is a trace of the curvature tensor. What's the meaning of the curvature tensor? The physical meaning, one of the most important properties of the Riemann tensor is that it gives you the geodesic deviation equation, that it tells you how neighboring geodesics move relative to each other. So that's what in physical terms is called the tidal force, how the tidal forces are. So if neighboring particles are attracted, or if they are repelled. And that's the property of the Riemann tensor. Now we have Ricci. Ricci is a trace of Riemann. And forming the trace is a kind of averaging over different directions. So if this is positive, or maybe zero, for this average quantities, this means that on average the geodesics become convergent. So in particular directions it is allowed that they become divergent, but then in the other directions they must become convergent in a stronger way. So the convergent property dominates. So it's a condition only on the Ricci tensor, not on the Riemann tensor. So it doesn't mean that in all directions the geodesics are made convergent. So that's what we usually observe. That under the influence of gravity, particles come closer to each other. They don't move away from each other under the influence of gravity. If you think of Einstein's field equation, then you can relate the Ricci tensor to the energy momentum tensor. So let me just write this here in brackets. If, and let's say the Einstein equation holds without a lambda term, if we have just this here, and let's assume that this is a dust, then this condition means what? Oops. Then the condition means that's the density. That's the energy density, but so this is the energy density with the c squared. So mu has a dimension of a mass density. That this plus p is positive, and also the trace, this is this here, plus 3p is positive. So this is certainly true if both the density and the pressure are positive. So that's what one calls a strong energy condition. If you write it in terms of the Ricci tensor, then you call it the convergence condition or something like that. But if you use Einstein's field equation and rewrite it as a property of the energy momentum tensor, then you call it the strong energy condition. So if density and pressure are positive, then this is certainly true. If one of them is negative, it's not necessarily true. And actually, remember, we considered the case that a perfect fluid mimics a gravitational constant, a positive gravitational constant. Do you remember what the equation of state was, the relation between P and mu in this case? And we want to mimic a cosmological constant? It was that P is minus mu c squared. Mu c squared was positive for a positive cosmological constant, but P was negative. P was minus mu c squared. So here this is just satisfied with the equality, but this is violated. This is violated, because this would be minus 3 mu c squared, And yeah, 1 minus 3 is negative, right? So this is violated. So actually, if at the very early time of the universe, yeah, in the immediate neighborhood of the Big Bang, if there was any, as a cosmological constant, which would be positive, then actually this condition would be violated. Yeah? But yeah, we don't believe that at the very early universe a cosmological constant played this role, or at least there's at the moment no indication in this direction. And so if really some kind of matter, maybe exotic matter, but some kind of matter dominated at the early universe, even before inflation, yeah, then one might think that this is a reasonable assumption. And anyway, at the time when Hawking proved this, most people thought that cosmological constants wouldn't play any role. And so then at this time, at least, most people thought this is a very reasonable assumption, actually. But one should be careful. There are some cases where it is violated. Yeah? Of course, it could also, we talked about mimicking a perfect fluid with a scalar field. If you choose the potential appropriately, you can also violate this condition with a scalar field. So there are meta models where this condition is violated, but they are somewhat exotic because they need a negative pressure. Okay, that's the first condition. So let's just assume that it is satisfied. So the second one, this is easily understood. There is a space-like compact three-dimensional submanifold. Let's call it S because I will quote it in a minute. And compact means compact without boundary. Yeah, without boundary. So it's really what is called a closed surface, three-dimensional surface without boundary. So examples would be, if you think of cosmology, the most natural, maybe I should use a different S here. Could be the three-sphere, yeah, as we have it as a natural topology for spatially closed Robertson-Walker universes, for Robertson-Walker universes with k equal +1, or it could be the three torus, so this would be S1, 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 or you could think of other topologies. Yeah? S1 cross S1 is the usual torus. Here's a donut, the kind of a ring. And then if you can imagine a third S1 attached to each point, then you get the three torus, which of course would live in a four-dimensional space if you want to try to embed it, so it's not so easy to visualize. So this means we live in, well, and that it is space-like means that you can use this as a snapshot of the universe. Yeah, the universe at a particular time. This would be that's the physical meaning of a space-like submanifold, and this should be compact and without boundary. That's the second assumption. So of course we have cosmological models where this is not satisfied. So this is only for this particular kind of cosmological models where we have space-like where the space is compact. At the moment, we don't know. We really don't have clear evidence either for one case or for the other case. The fact that we are fairly sure that k is different to 0, the capital K is a curvature, if we make the assumption that Robertson-Walker is a good approximation, this does not mean that the universe is not compact. Yeah? Because you can form out of a spatially flat universe, the natural topology would be R3. But you can roll up the axis and then you get a torus. Yeah? Actually, people are looking in the cosmic background radiation for a signature which comes from such a topology. So this is not out of the question. Even if we assume that for the Robertson-Walker approximation the k is 0, even then it's not ruled out that the universe is spatially compact. Well, and the third assumption, yeah, we must formulate the fact in a certain way that the universe is expanding at a particular time. And for this particular time, of course, we use this submanifold, which is a time, as I said, a snapshot of our universe. Let me draw it this way. But you should think of something which is closed, yeah? Something which is compact without boundary. So then we can, and it's space-like. By assumption, it's space-like. So if I take the normals at each point, they are time-like. Yeah? They are time-like. So they define, and then I extend them geodesically. Yeah? So I draw the geodesic from each point of S. I draw the geodesic which starts perpendicular, and I draw it into the past. This gives me a vector field, V, so if you use coordinate language, then it would be something like that. Yeah, this would be a vector field, a geodesic, time-like vector field. Time-like, because S is space-like. And now the question is, what you want to formulate is that this vector field in this direction converges. Yeah? This would mean that the universe is expanding at this instant of time. So how do you formulate the fact that neighboring integral curves of this vector field V approach each other? So they come closer to each other. Well, if d mu is the time-like geodesic, time-like past-oriented, time-like past-oriented vector field, geodesic vector field. Geodesic vector field means the integral curves are geodesic. Yeah? Geodesic vector field perpendicular to S then I can form the following expression. I take, well, let me begin with this here. If I take this, just the covariant derivative. This tells me how neighboring integral curves, if I measure this with, if I measure changes with the covariant derivative, then this tells me how neighboring integral curves of V change if I differentiate in a certain direction given by this index here in the direction of the basis vector field d by d mu. And if I now take the trace about this, over this expression, then I average over all directions. And that's what one calls the expansion. Yeah, that's the definition of the expansion of this vector field. It's usually denoted theta. Actually, the quantity theta we were discussing for the Bianchi models last time was exactly this theta for the vector field perpendicular to the surfaces of equal time. And now the statement is, then this here then satisfies. So this is a function on this domain. Yeah, at each point I can calculate this function, and it tells me if neighboring integral curves of V come towards me or move away from me on average. That's what this quantity tells me. And the statement is that they should, on average, they should come together. So the expansion should be negative, right? So theta on S, that's the initial condition. Yeah. If I just consider points on S, then this is strictly smaller than 0. Yeah, so it's converging. Converging everywhere. So the expansion is negative. So that's a way of mathematically formulating the statement that our universe is expanding at this particular point, which is given by this time slice S. Nothing is said about homogeneity or isotropy. So just the fact that this quantity theta is smaller than 0 doesn't mean that the expansion is isotropic or that it is homogeneous in any sense. Yeah, it may depend on the point. In general, it will depend on the point. Arbitrarily strongly. It's also nothing said that it's just a small perturbation of homogeneous or isotropic models. So the deviation from homogeneity and isotropy can be arbitrarily large. It must just be in a way that at each point, on average, I have a converging initial condition. So in this sense, the universe is expanding everywhere on this initial hypersurface S. And then the statement, if you accept these three assumptions, so the first is an energy assumption. So the energy momentum tensor should have more or less reasonable properties. As I said, there are some reservations about this, but let's assume this. Then we are living in a closed universe. Let's assume this as a second assumption. And then we have an initial condition where the universe is expanding in the future direction, so it is converging, and the V is converging in the backward direction. And then the statement is space-time is singular. So actually in this, for this theorem, one can formulate it in a more more precise way, we had defined a singularity in general by considering time-like or light-like geodesics. So the statement was just one of the two classes of geodesics would be incomplete. Here we can say that it must be the time-like ones. Space-time cannot, let me write it in this way, cannot be time-like geodesically complete. So here it is really the proper time along the world line of freely falling particles which which come to an end backwards in time at a finite time. Space-time cannot be time-likely geodesically complete. Okay, sorry, not sure if you can read this. And then come the three conditions. At this time, this really came as a surprise. So, well, this was the second theorem in the row, so Penrose already had proven something similar for the collapse of stars, but even so, it came as a surprise that actually the fact that there is an initial singularity, in the sense that time-like geodesics start at a finite time. So there are observers, yeah, these integral curves of the vector field V, they could be interpreted as freely falling observers, and if you extend their world lines backward in time, and you see they start at a finite time. So for them, the universe began at a finite time. In this sense, there was an initial singularity. Nothing is said about a density becoming infinite or about a curvature becoming infinite. This is not said. And actually, after this work was done, after 1970, then people started to investigate the nature of the singularity. So under what conditions can we say that it is a curvature singularity or that a density becomes infinite? And this was, not really successful, actually. So there are not very strong results about that. So what the Hawking-Penrose theorems tell us is just the existence of a singularity in this sense. And so this was for the spatially compact case, where I think the three conditions are easily understood. And now it's up to you if you are willing to accept them. Yeah? Then you have to accept the result that there was an initial singularity. Of course, Hawking also tried to do it for non-compact slices. So if we don't have a compact, if you don't assume that space is compact without boundary, and then actually even the formulation of the theorem is more complicated. So this was theorem one, we call it this way. And let me also quote the second theorem. It was in the same paper, the third paper of the series. So, and in this case, I think it is time-like or light-like. Is time-like or light-like geodesically incomplete. If the first condition is exactly the same. Yeah, we have again the strong energy condition. If you write it in terms of the energy momentum tensor, no, we use Greek indices. This is positive, it means converging if the vector is light-like or time-like. And now the second condition. So I said the second type of condition in these theorems is either a topological assumption, that was here the case. We say the space is compact, that's about topology, or it is a causality assumption. And in this case, it is a causality assumption. There is a point P, where, as one says, a strong causality condition holds. I'll explain in a minute what this means. Where the strong causality condition holds. What does this mean? Well, the weak causality condition, or the chronology condition, this means that if you are at a certain point and you consider all time-like curves which start from this point, then none of them will come back precisely to this point. So there's no closed time-like curve to this point. This is what one calls the chronology, or the weak chronology condition. And causality means that you also consider light-like curves. So for time-like and light-like curves, you don't have closed curves to this point. Now people soon realize that there are spacetimes where this condition holds, where you cannot have a time-like or light-like curve which comes precisely back to the point, but where it comes back arbitrarily close. Yeah? So if you choose any neighborhood of the point, however small, then the time-like closed time-like curves will come back into this neighborhood after a while. They will never hit exactly the point P again, but they will come back into any neighborhood, however small you choose it. And if you exclude also this, then you say you have strong causality. So this means there is no neighborhood. Or wait a minute, there is a neighborhood. There is a neighborhood of P such that no closed causal curve comes back into this neighborhood. So in particular, there's no closed time-like curve through this point P. Of course, well, you know what closed time-like curves mean. It means that, you can travel into your own path, so you could now decide that I travel into my path and then I kill my father before I was born, yeah? And then you have this famous logical contradiction. So at least as if the total travel time for such a closed time-like curve is so short that it can that you can cover it within your lifetime, then you really come into logical problems if you assume that there are such closed time-like curves. If the travel time is so big that you need, I don't know, much longer than your lifetime, then you wouldn't run into this problem. And with this loophole, some people say we might be willing to live with closed time-like curves if they are just big enough, but usually one excludes this possibility. And so let's assume, so for this version of the theorem, we assume that there is a certain causality condition satisfied. And then the third condition, well, we need some kind of initial condition that in the backward time, the universe is collapsing. In the future direction, it is expanding. Now we don't have this initial surface S in this case. And so we have to formulate it in a different way. And actually, this is now formulated in it's a little bit more complicated, so I first draw a picture, then I write the statement. So in this case, we choose this point P. It's the same point we have used here in the second statement. And instead of considering geodesics which start perpendicular to an initial surface, now because we don't have an initial surface with nice properties, we just consider all geodesics which start from this point P into the past. Yeah? So they will again define a vector field V. Yeah, we write it here, which is it is time-like onto the interior of this cone, at least for initial conditions. They form a cone, the interior of a cone. And for them we can also formulate now the expansion. So we can formulate the statement that they are made reconverging under the influence of gravity. That's what we want to formulate. So we want to have a negative expansion. But here in this case we need a stronger statement than that. So just requiring that the theta would be negative is not strong enough. Actually, the theta must be bounded away from zero. Yeah, it's not enough just to requiring it to be negative. It must be bounded away in a certain way from zero in order to prove the theorem. So the statement is a little bit complicated. So the statement is there is a time-like, past-oriented, or past-directed, let's say, past-directed vector, say, W mu at P, such that for the past-oriented time-like geodesic vector field W mu, this is what I've drawn there, issuing from P. We have the following conditions. The theta must become smaller than minus B over C. No, there must exist a constant B. I have to write it in this way. There is a constant. Oops, statement is a bit complicated. There is a constant B bigger than 0, such that theta, it's the same theta as we had before. It's the expansion of this vector field, satisfies theta becomes smaller than minus B over C within a distance let me see. No, minus 3C over B. Minus 3C over B within a distance B over C from P. Where this, I've said B is a constant, a positive constant, but what is C? C is minus W mu V mu at P. This is positive, yeah, because both are time-like and past-oriented. So if I have two past-oriented vectors, which point, they point into the same half of the light cone, because both are past-oriented. So this is negative, with a minus sign it's positive. So this means theta must be in particular negative, yeah? But it must not be smaller than, it's not enough to require it to be smaller than 0. It must really be bounded away from 0 by this constant. So if I follow an integral curve of V into the past, then before I reach this limit, B over C, before I reach this limit, my theta must have become smaller than this value, minus 3C over B, which is negative. Yeah? C over B is positive, so with a minus sign it's negative. So in particular, theta is smaller than 0. So it's a way of requiring that the time-like geodesics issuing from this point P, that they are made convergent under the influence of gravity if I follow them into the past. And then the statement is a singularity is formed. Okay, so this is a way of saying that the universe in a sufficiently small past of this point P is expanding, yeah, because this means that these geodesics which issue into the past, that they are made converging. So if you follow them into the future, then this is a way of saying that the universe is expanding. And then we have a past singularity. So the singularity is actually the way in which you prove this is that you prove that one of these geodesics become incomplete. Could be the boundary case, the light-like case. I think in this case it could be the boundary case. So you cannot rule out that it just happens for a light-like geodesic. Okay, so these are the theorems, and in both cases you see no symmetry assumption. No other particular initial condition. It's just inequalities. Yeah. So in this sense, the conditions are generic. They are generic if a certain inequality is satisfied. So you don't do some kind of fine tuning. Yeah, that you choose the initial condition in a particular way, or you assume particular symmetry. So it's an interval. It's an interval for values where this is satisfied. So in this sense, it is generic. Yeah. So what these theorems taught us was really the main result of these theorems was really that singularities are in a certain way generic. And now the question is, how do we interpret this? Are you willing to live with this result, or would you draw the conclusion that something is bad with the theory? Maybe we should look for a better theory which doesn't give us these singularities. And what most people believe is that these singularities will go away, or they will be of a completely different nature if we combine this classical theory of general relativity with quantum ideas. Yeah, if we do some kind of quantum gravity, that then the singularity which appears with a collapsing star and the singularity which seems to be there at the beginning of our universe, that they will be of a different nature. And there are some versions of quantum gravity theory or quantum cosmology, maybe to put it more precisely, where this is loop quantum gravity, what I'm referring to, where actually what appears in a classical picture to be a Big Bang is actually something like a state where the universe comes very, very close to a singular state. But it isn't singular, it is just then re-expanding and becoming our universe, but it's never become zero. Yeah, so the volume, so to speak, never becomes zero. So in loop quantum cosmology, you can form some models of this kind, but well, one should say this is highly speculative. So the whole theory is not in a state that one could say this is really established or it made contact with observation or experiment in a satisfactory way. But at least there are theoretical ideas, theoretical hints in this direction that if you include quantum ideas, that then the initial singularity might be avoided. So that's the way why most people say it's not really necessary to be too much troubled about these singularities. They are there in the classical theory. Okay, I don't say anything about the proofs of these theorems. The proofs are very, very complicated. Actually, 2 times in my life, I gave courses just on the singularity theorems. And in both cases, I did not manage to prove all 4 of them. When I did the Penrose, this is, as far as the proof is concerned, I think the Penrose one is the simplest, the first one. So in both cases, I managed to do this completely, and for the other 3, I just had to, I had to omit some details. Also, you need a lot of terminology just in order to get the tools for the proof, which you need. Yeah? So you need to know something about Cauchy surfaces and about Cauchy developments and about horizons and things like that. So a lot of mathematical apparatus is needed. There's a book about this. Maybe some of you have heard about this. Not by Hawking and Penrose, but by Hawking and Ellis, Hawking and George Ellis. They have written a book in 1973, I think, which is essentially about the singularity theorems, also about other things, but they play a central role in this book. It's called The Large-Scale Structure of Space-Time. And even there are some, the proofs are not absolutely complete. Yeah, there are still some gaps. People have found some gaps in this, and they have worked on details even after the book has appeared. Then there's a textbook by Wald, which discusses the singularities in great detail. And what I mentioned already, the mathematical textbook by Beam and Ehrlich also has chapters on the singularity theorems. So in my view, this is one of the most intriguing developments of general relativity, which was just at the center of the debate at the time when I entered this field. Yeah? So I came to relativity in the mid-70s or so, late 70s, say. And at this time, it was really it was in the discussions and all kinds of conferences. You came across these theorems, and they were vividly discussed, and and they influenced the further development strongly. Okay, so this is an open issue, as I said. It will be really settled probably only when we have a quantum theory of gravity. But that's the status how it is now. And as I said, I couldn't end this course on cosmology without saying at least a few words about the singularity theorems. That's what I tried in this. It was 60 minutes now, not 45 minutes. But anyway, so from my side, I would stop here. But maybe you have some questions which we could discuss. It would be an opportunity.
Yes. As much questions as maybe a remark. I heard that if you have these real small space quanta, so the universe goes through there without becoming a singularity, that gamma ray bursts give off their radiation frequency dependent, like there's how do you call that in radio astronomy? Dispersion, something like a frequency dispersion, and this was not observed. So people think that the space quantum must be smaller than the Planck length.
Okay.
About that.
Okay. I'm not sure if this was understandable over the microphone, so let me repeat this. The remark was that if we assume that these ideas from loop quantum gravity are correct, that actually what looks like a Big Bang in this classical picture is actually only a state where the universe is very small. Let's say something like a Planck length. That then, this was a statement, that then gamma rays should have been emitted at this very early time of the universe, and probably under the influence of when this gamma ray burst travel to us, then dispersion would occur. That dispersion is something which usually occurs in a medium.
Yes, somehow on frequency sorted, like radio radiation comes in frequency dependent.
Yes. Yes, that's something which is very familiar, say, from pulsar observations. Yeah, the signals from pulsars, they show this dispersion because of the influence of the interstellar matter. So the travel time depends on the frequency. That's what one calls dispersion, right? And of course, this would also be the case for these gamma rays, which would have occurred at the early time of the universe. And apparently, one hasn't found this kind of signature. Which, okay, I've never heard about this, but it's okay. Okay. Space quantum. Yeah. Okay. Yeah, I think one should really credit these people who are doing this quantum cosmology approach, because they could make at least some kind of contact with observations. This is something which I think I'm not unfair when I say that the string people never have come to this state. Yeah, the loop quantum gravity have been able to make at least a little bit of contact with observation, and this issue which fits into this discussion. So actually, I've never done any work in quantum gravity, but if I would work on quantum gravity, then I would probably go into loop quantum gravity. So this seems to be the most promising. Not really promising, but maybe more promising than the other. But it's, of course, it's a matter of taste. It's a matter of taste, yeah. Of course, the string people would completely disagree with that. So they are very enthusiastic about this subject. And from a mathematical point of view, they certainly also have very good reasons for this. But they have the big problem that they cannot make contact with observations. Okay, so I cannot say anything more specific to this particular issue. Any more comments or questions? So if not, then I say goodbye to everything, also to those who are watching us. And then we have, I wish everybody a nice summer break. Okay, see you.